So today is probably the last video doing some problems with Newton's laws of universal gravitation. And we'll start off thinking about the International Space Station. And the International Space Station, the ISS, orbits at 4.09 times 10 to the 5th meters above the Earth, which is about 254 miles. 254 miles. And you can actually see it sometimes when it makes a passage across the sky. I haven't personally seen it, but I've seen videos of it. Now, the problem is that distance that they gave us is not the distance from the center of the Earth. We have to add the radius of the Earth to the distance where the satellite is. So that's what I did in the first step. I took the 4.09 times 10 to the 5th, and the radius of the Earth is 6.38 times 10 to the 6th meters. Now, it's not a uniform radius because the Earth does vary a little bit, but close enough for what we're working with. Now, if you remember, we set mg equal to the law of universal gravitation. We've done this at least 2 or 3 times. And the mass of the satellite cancels out because we don't know the mass of the International Space Station. They didn't tell us. Then all we have to do is substitute. G is the G from big gravity, gravitational constant. M is the mass of the Earth. We didn't worry about the mass of the satellite. It canceled. We got rid of that. And then we divide it by the total distance, and we're going to get a surprising number, 8.65. We think that people are weightless on the Earth, or on the satellites. They're not. What's really happening is that the satellite is being pulled in a circular orbit, and so are the astronauts. So it's really more like the floor is falling away from them. Might be a better way to think about it, because they're not truly weightless. I mean, that G is a little bit less than what it 9.8, but not as much as you might think. Maybe only 10 or 15% less. To be truly weightless, the astronaut would have to go way, way far away from the Earth. So we're talking, like somewhere out between Earth and Mars or something. So it's a surprising value. Another thing that we know is that objects, we'll take a look at the moon, are about 1/6 of their weight on Earth, or that what they are on Earth is what they are on the moon. So let's see if we could calculate the mass of the moon, knowing the radius. So first order of business, here's the moon, is they give us the radius, they give us the R value, but it's in kilometers. So we need to flip that over into meters. Another thing that we can do is we can know that gravity on the moon, they just told us, it's about 1/6. So we can take the 9.8 and divide by 6. Now I have this formula, we just did it in the last slide. I'm not going to re-go through it again, and we want the mass. So I'm going to multiply by both sides over r squared times big G. They get m is g r squared divided by big G. Now it's just a matter of substituting. And remember, we're using these values for the moon. And we get that the moon is 10 to the 22nd kilograms. Remember, the Earth was 10 to the 24th. So the moon is on the order of 100 times less. It's actually, it takes 81 moons, so that's close to 100. It takes 81 moons to equal the mass of the Earth. And we're doing all this with calculations because there's no scale that we can put the moon on. Now, let's go to Mars. So we had, I don't know, I just chose a pug dog because they're cute. Weighs 200 newtons on the Earth. Then we want the acceleration of gravity on Mars and the weight of the pug on Mars. And they give us some information here. They give us the radius of Mars. They give us the mass of Mars. They say it's 0.11 times the mass of the Earth. So that would be 0.11 times 5.98 times 10 to the 24th. And I have some space on the next slide to do that. So let's see what we can do. G is big G, m, r squared. So big G doesn't change. 6.67 times 10 to the 11th. Yep, that's what it is. 10 to the minus 11th, excuse me. Now we need the mass, but the mass of Mars, which is 0.11 times the mass of the Earth. 6.58 times 10 to the 23rd kilograms. So we'll put that in. I apologize for flipping back and forth between the slides, but that's how I have it set up today. Then the radius, now that's in kilometers. No problem. That's kilometers. We multiply it by 1,000, which is 10 to the third. And don't forget that we're going to square it. So we're going to be able to get G there. Let's get the number. And you can hear I'm just entering in my calculator here. I just put 3440 times 10 to the third and square that. No problems in my calculator. And it turns out that the pull of gravity on Mars is a bit less than what it is here on Earth. It's only 3.71 meters per second squared. Now let's deal with that pug. He's 200 newtons. That's a weight. So weight is mg. We want his mass. The reason we need the mass is because weight can change. Mass cannot. We assume the mass is the same. So 200 newtons divided by 9.8 should be around 20-ish. Let's see. Yeah, 20.4 kilograms. Now on Mars, his weight will still be mg. However, it's going to be the gravity that's on Mars. So 20.4 times 3.71. So on Mars, he'll only be 75.7 newtons. The weight will have changed, but not the mass. Now let's try one more here, and then we'll probably wrap this up. So let's get the acceleration due to gravity on Pluto. And let's see if they're good enough. Yeah, they give us all the information here. They give us the mass of Pluto. It's a lot less than the Earth. Now watch, the radius is in kilometers. We need to multiply by 1,000. So this is really just plugging the numbers in. And wow, look at that G value. That's almost nothing compared to Earth. There is gravity on Pluto, but not very much. Now the person weighs 550 newtons on Earth. So we're going to need to calculate their mass. Weight over gravity. Just like we did in the previous video. And I don't know what that's going to work out to. 56 kilograms, 56.1. But on Pluto, we'd use mg, but not that of Earth. We would use the 0.628. So on Pluto, instead of weighing 550 newtons, as they do on Earth, only 35.2 newtons. Much, much less. Now, let's do the last problem, but I need a little more room here on the slide. So if you need to see any of this, go back and just watch that part of the video again. Move the little slider back. Here's the sun. We want the orbital speed. So we know the distance, 5.9 times 10 to the 9th kilometers. If we multiply that by 1,000, which we're going to need to, we'll get that in meters. And its year is 248 Earth years. It's how long it takes to go around. So remember, it's going in a circle. So the distance is actually the circumference, which is 2 pi r. So the distance is 2 pi times that really big number, and I'm going to do it in meters and see what it is. Because it's a circle. The path is a circle, so we have to say how long does it, or how far is it to go all the way around the circle? And it's a nice big number, 3.71 times 10 to the 13th meters. Now, here's the real pain. We've got to take our 248 years, so 1 year is 365 days, 1 day is 24 hours, and an hour is 3,600 seconds. We've got to take and get the seconds, and it's going to be a huge number. So the time is 7.82 times 10 to the 9 seconds. Now the speed at which it goes around, the v, is just distance over time. 3.71 times 10 to the 13th over 7.82 times 10 to the 9th. So we had to do all these really big numbers. And we get 4,740 round with significant figures meters per second. That's how fast Pluto is going. And in fact, if the sun were to disappear, Pluto would go off in a straight line at 4,400 or 4,740 meters per second.